Well, as promised, we're going to return now to the topic of fingerprinting with a talk by Pouneh Bahrami, a Ph.D. candidate at the University of California, Davis. Pouneh's research focuses on browser privacy and security, and she's going to tell us about leveraging machine learning for early detection of new browser fingerprinting methods. Pouneh, welcome to the Adblocker Developer Summit. We're excited to hear about your research.
Hi, thanks for the introduction and welcome to my talk, FB Radar, a machine learning approach to systematically detect novel abuse of web APIs for fingerprinting. This is a collaborative work with Omar Iqbal and my advisor, Zubair Shafiq. This work focuses on a particular type of online tracking called browser fingerprinting. Peter had a great talk today about fingerprinting, but let me give a real quick overview of browser fingerprinting. Online tracking can be broadly divided into two categories: stateful tracking and stateless tracking. Stateful tracking is deterministic. Trackers store identifiers at the client side using cookies or other types of local storage. They're ideal for tracking, but they're directly observable by users in the browser and can also be easily removed. And also several browsers have progressively restricted useful trackers, such as third-party cookies, and trackers cannot circumvent these restrictions. These issues with stateful tracking have motivated trackers to move toward a more invasive form of tracking called stateless tracking. Stateless tracking or browser fingerprinting is not as simple as stateful tracking because it is not deterministic. To extract a fingerprint from the browser that can be a useful identifier, it needs to be first unique. It needs to capture enough distinguished information to uniquely identify a user. And second, it needs to be stable. If it changes, then it needs to be linkable over time. Stateless tracking has some clear advantages compared to stateful tracking. Fingerprinting doesn't lend itself to transparency and control. Users cannot easily observe or remove their browser fingerprint. And more importantly, it is a moving target. It has continued to evolve over time as browsers support new functionality. As browsers have added new APIs or updated existing APIs, the browser fingerprinting service has continued to expand. So this highlights the need for novel detection approach for evolving fingerprinting techniques that abuse web APIs in novel ways. Let's look at an example. In this simple example, a JavaScript snippet is embedded in a website. 3 different users visit this website, and the JavaScript code runs on their browsers and extracts a number of information from their browsers. For example, navigator.hardware concurrency returned the number of processor cores available on user system, or navigator.language returned the languages known to the user. And the value returned by the mentioned properties of Navigator gathered distinguishable information in the server side. So as you can see in the database of the tracker, these 3 users are distinguishable. And trackers gather different information at the client side using different APIs supported in web browsers, and then exfiltrate this information to the server. Next, let me talk a little bit about some of the issues of existing state-of-the-art browser fingerprinting detection mechanisms. Cookies are straightforward to detect and block because they are right there in the browser, but it is not that straightforward to detect and block fingerprinting because you need to do a sophisticated dynamic and static analysis of a JavaScript which has implemented the fingerprinting technique. The process of detecting fingerprinting techniques used to be manual previously using heuristic approaches, and this approach detects fingerprinting script with a predefined heuristic, which is narrowly target fingerprinting script. But they have this approach or heuristic has some limitations. For example, designing a heuristic is laborious and time-consuming. It is brittle. They may miss fingerprinting script that do not match the narrowly defined detection criteria. And also, they don't work for evolved or new APIs because it is predefined based on known fingerprinting techniques. And finally, they reactively looking for known fingerprinting techniques in one point of time. Princeton Web Transparency and Accountability Project is an academic project that provides some heuristic to create a certain type of fingerprinting, such as Canvas or Web API. The second approach of detecting fingerprinting technique is learning or ML-based approaches. Technically, they try to learn tracking behavior of a script based on their structure and execution. They automatically extract features, and in contrast to heuristic approach, they are flexible to minor changes. And same as heuristic approach, they are not designed to detect new or evolved APIs. They reactively looking for known fingerprinting techniques in one point of time. FP Inspector is another academic project that detects fingerprinting scripts automatically. So in summary, what we have discussed so far is that existing detection mechanisms are limited to reactive detection of a script that implement known fingerprinting techniques. So systematically, they're not designed to detect new fingerprinting techniques. Next, let me talk about our method, FP Radar, which addresses the aforementioned limitations. FP Radar is able to detect abuse of newly introduced properties of already known APIs, such as WebGL or sensor, as well as previously unknown APIs, such as gamepad and clipboard. It consists of 4 components. I will go through each step in the next couple of slides. As I explained in the beginning of this talk, browser fingerprinting is an evolving phenomenon. As new APIs are introducing, it is reasonable to expect that they might be abused for fingerprinting. FP Radar operationalizes this evolution in a longitudinal fashion to capture temporal trends in Web API usage and early detection of Web API abuse for fingerprinting. To longitudinally analyze Web APIs, FP Radar needs to measure their usage on web over time. But the problem is that we don't have access to the history of websites. To gather historical snapshots of popular websites, we rely on Internet Archive's Wayback Machine. We extract the list of a script present on Alexa top 100K websites, and then we request the Wayback Machine to crawl historical snapshot of scripts URL during 10 years, and we keep their content in our dataset. So what we have so far is a separated dataset of JavaScript files for each year. FP Radar or our method relies on guilt by association, principle of guilt by association, to detect the abuse of web APIs for browser fingerprinting. It means that if an API is being used alongside known fingerprinting API, then we can presume that the API in question is also being abused for browser fingerprinting. So to model this principle, we present Web API co-occurrence in a graph. Let me make it more clear using an example. Say we have 3 different JavaScript files. JavaScript are written by different developers. 2 scripts with for example, 2 scripts with the same functionality might have different coding styles, but we want a consistent coding style. And to address this issue, we present a script as abstract syntax trees or ASTs. And this allows us to ignore coding style differences between scripts. Moreover, we are only interested in API keywords that match standardized web APIs. So to reduce the complexity of a script, we traverse AST tree and only extract and keep API keywords out of JavaScript files. And finally, we model extracted API keywords as nodes and include an edge between the nodes if the API keywords co-occur in the same script. Next, we weigh the edges between the edges based on the co-occurrence frequency. As an example, if you consider canvas and fill text, which are extracted two nodes, which are extracted from the most left file and also the middle file, they have connected to each other and their edge weight is 2 because they have co-occurred in two JavaScript files. So please note that we create an individual graph for each snapshot, and in total we have 10 graphs starting from 2010 to 2019. To help every writer's goal of early detection of web API web abuse for browser fingerprinting, we try to predict API concurrence in the future. So for this, we leverage longitudinal connectivity of APIs with each other to predict their connectivity or their future connectivity. Let's have a closer look at graph prediction procedure. Suppose we have real graphs in 2010 and 2011, and we want to predict the concurrence graph, which is going to form in 2012. We implement an embedded based classifier based on the features of previous real graphs to predict the forming graph in next year. And our intuition for relying on these features is that the existing connectivity of APIs is indicative of their future connectivity. So we repeat this process, predict the API concurrence over 10 years by iteratively building temporal graphs. So we continue our detection and continue our detection and analysis based on the predicted graphs. FP-Radar's temporal graph allows us to longitudinally investigate the evolution of web API concurrence. Let's have a closer look at our temporal graphs. Here we have our temporal graphs predicted, temporal graph starting from 2010 to 2019. FP-Radar non-temporally clusters the graphs based on the Loovian method, and then it links clusters across consecutive years together to form temporal clusters. Specifically, FP-Radar link together if their Jacquard similarity is more than a threshold. So in our case, it was 30%. Now let's take a look at our measurements and results. In total, we extract 14 temporal clusters. Each row of this table shows one temporal cluster. So the number of keywords in each cluster, as well as the lengths of temporal clusters available in the first and second column consecutively. For example, the first row shows that one of our temporal clusters has 313 API keywords, and also the lifespan or the length of this temporal cluster is 9 years. We don't have a precise ground truth which clearly states which API keyword is fingerprinting or non-fingerprinting, but there is an open source browser fingerprinting library, Fingerprinting.js, that implement most of the fingerprinting techniques. And there are a lot of studies showing that this FP.js library is being used directly or with some changes by fingerprinters. So we use FP.js as our ground truth to label a cluster at each snapshot as a cluster of fingerprinting keywords. And then we find the intersection of keywords in each cluster with the keywords appearing in FP.js library and compute this percentage. So as you can see in the third column, the first temporal cluster has the most number of fingerprinting keywords. So we flag it as a fingerprinting temporal cluster. We expect functionality-related APIs appear together in a temporal cluster. To this end, we use MDN's hierarchical taxonomy to map each API keyword to one of the 88 APIs on MDN web documents. And then we identify the dominant APIs of each temporal cluster using this taxonomy. We measure the dominance of API in a cluster as a fraction of its keyword that exists in the cluster. For example, the dominant APIs of the fingerprinting temporal cluster are battery, navigator, and network information, for example. And most of the APIs you can observe on this temporal cluster are usual suspicious fingerprinting APIs, such as battery, navigator, or canvas. But we don't want to waste your time on the things you already know, so I just focus on our new findings. And in the next couple of slides, we do a deep dive into 3 selected dominant APIs of the fingerprinting temporal cluster. So one of these APIs that we observed in the fingerprinting temporal cluster is page visibility. It's released in 2013, and it is an API that provides access to visibility state of a document. For example, it can say that whether a tab is visible or hidden to a user, and meanwhile, it is triggered as soon as a user switches between tabs or windows. Our investigation shows that this API is not directly used for fingerprinting, but can be used for ephemeral fingerprinting. FBRadar detects this keyword as early as 2013, right after it was supported in major browsers, and as far as we know, it's not disclosed yet. But let me bring an example to show that how it is being abused by fingerprinters. Suppose a user has 2 tabs in their browser, but only one of them is visible to them as an open tab. If they click on the next tab, then a change in visibility state will be simultaneously triggered for both tabs. So basically, the first tab is going to be hidden, while the second one is going to be visible. And this will happen real quick in less than a second. And this information can be correlated by a script on both tabs to link whether the tabs are on the same browser. And the time and steps when page visibility state changes is expected to be same and distinctive across all co-visible sites on a user's browser. So it can be used to build a cross-site ephemeral fingerprinting. The next API that appeared in fingerprinting cluster is Gamepad, which allows browser to connect to gamepads. And get gamepad, a method of this API, return the list of gamepad objects as well as their configurations, such as, for example, access, buttons, display ID, or hand. Our analysis shows that fingerprinters first probe whether browser has a connected gamepad, and if there's one connected, they collect the mentioned configuration information, and this information can reveal distinctive information about the browser. FBRadar detects these keywords as early as 2014, right after it was supported in major browsers, and it was disclosed 6 years later, actually. Like, for example, starting from 2020, Mozilla requires third-party iframes to ask for permission before calling the get gamepad method. And the last API I'm going to talk about is Sensor API. A lot of study has been done on identifying users using sensor information, and these studies dates back to 2014. But the point is that all the studies are based on an old interface, such as device motion event and device orientation event. And this interface is able to, for example, gather information about the change in motion using accelerometer. But These interfaces are not part of sensor APIs, although they have similar methods and properties. But sensor API is like separate interface or API, and it is still updating, and it is approximately a new APIs, and it is supported by Chrome, but not Firefox and Safari. FB Radar detects the use of number of new features of Sensor API in 2017. For example, ambient light sensor, which returned the current level of the light around the hosting device, and it is not part of old interfaces, as I mentioned. And as far as we know, it is not disclosed yet, so it is like a new API. We have a small subset of APIs and their corresponding keywords here. For example, you can see navigator and number of its methods and properties here in the blue box. Let's consider hardware concurrency, which simply returns the number of cores on a CPU. It was released and supported by major browsers starting from 2014, and it was publicly disclosed as fingerprinting keyword in 2017. And it appeared in our dataset for the first time in 2014 and detected by FB Radar as its first appearance also in 2014. So depending on the time of our detection, in comparison with the disclosure date, we categorize these keywords to on-time detection, early detection, late detection, and for a number of keywords that there isn't any public disclosure, we color them with green. And finally, there isn't any comprehensive ground truth to compare our results to, but we compare FB Radar's fingerprinting API list with DuckDuckGo's list. DuckDuckGo's Tracker Radar project published a list of suspicious APIs each month, so they update it monthly. And based on our discussion with DuckDuckGo, the list is limited to about 100 keywords, and they use a simple heuristic to detect fingerprinting scripts. FB Radar's fingerprinting keywords cover about 80% of their detected keywords, but meanwhile, our list includes 700 more keywords, and many of which are clearly being abused for fingerprinting. So we believe that our method or FB Radar can enhance the DuckDuckGo's list of fingerprinting APIs. FB Radar can also complement and improve fingerprinting script detection tools like FB Inspector by making it more proactive. So we are planning to open source FB Radar as well as its data, and we hope that the community will build on it to improve countermeasures against browser fingerprinting. And also, I would like to let you know that I'm looking for an internship for the coming summer. So if you're interested in my work, I hope we can connect at some point. And thank you for your listening, and your questions are welcome.
Yeah, Pouneh, thanks so much for that. We do have several questions for you. Let's start with a simple one that we've got. Earlier, Pierre Lowe mentioned fraud prevention as maybe the one benefit of browser fingerprinting. We've got somebody just saying, other than that, are there any other upsides to browser fingerprinting, or is it pretty one-sided?
You mean the positive aspect of fingerprinting? Sure. I think, yeah, as far as I know, the only positive, at least based on the analysis of a script that we have, the only intention or good intention that we detect is just for security or fraud detection. Other than that, yeah, I can't say anything.
We've got another one here that's come in our chat from Ben Standard. Ben's asking, he says, many of the fingerprinting scripts can come from third-party ad networks, and they need to be each time the page is loaded. How does that impact the way that you understand the data from the Wayback Machine?
Sorry, could you say that again?
Sure. So in the chat here, Ben's asking, he's mentioning the fact that the fingerprinting scripts that are present on a lot of sites come from third-party ad networks, and they have to be loaded each time the page is loaded. So how does that impact the data that you've used from the Wayback Machine?
So basically, we use Wayback to like collect the data to be able to see the trend of web APIs. For example, suppose suppose a website like Facebook, we wanted to make sure like how they use or what is the evolution of using APIs during, for example, 10 years. So the only like reason that we use Wayback was to see this trend or trend of using different APIs. So for example, what happens to gamepad is that we figure out that it is not just by accident. It's about, for example, 6 years that this API is being used for fingerprinting, but we disclose it after 6 years. So that's the reason that we use Wayback actually.
Yeah, that makes sense. And now that we've talked a little bit about the past, we've got a question asking about the future. Where do you see browser fingerprinting going in the next few years?
Like at least based on our analysis, we expect that many APIs as they are introducing being abused by fingerprinters. So we believe that at least for example, something like our method Epirator is able to detect this unknown APIs, and I think we should be ready to expect that fingerprinting is not limited to known techniques. There are many aspects of this API that are being abused by fingerprinters.
Wonderful. Pouneh, thanks so much for your presentation. I think that yours combined with Peter's and Ray's from earlier gave us a lot of really good insight and like a rounded perspective into ways to tackle fingerprinting going forward. So thank you for taking the time to share your research with us today.
Thank you for having me.